A new security narrative is emerging around the Apple M5 chip, claiming a first memory exploit discovered using Anthropic AI grants root access. The stakes are high because if this is true, the fundamental trust in silicon-level security for AI workloads is shattered. By the end of this video, you will understand why this specific claim is a misunderstanding of how these systems actually work, and more importantly, where the real, tangible danger lies for every developer building autonomous agents today. There is a lot of buzz right now about a supposed vulnerability in the M5 architecture. Headlines suggest that researchers used an AI model to find a flaw in the neural engine that allows it to bypass memory protections and seize root privileges. This sounds like a catastrophic failure of hardware design. It suggests that the very mechanism designed to accelerate your machine learning models is now a weaponized backdoor. But here's the thing. The reality is far more nuanced and actually more instructive for you as a practitioner. The M5 chip has not been released to the public, and no such hardware-level exploit exists in the current literature. The confusion stems from conflating authorized high-privilege tooling with a genuine security breach. When we talk about the M5, we are talking about a future architecture that Apple has not yet unveiled. The neural engine inside that chip is designed to handle massive parallel tensor operations with incredible speed. It requires a specific memory region for weight buffers to function efficiently. In the current generation of chips, we have seen vulnerabilities where these weight buffers lack the same isolation guarantees as the standard CPU memory managed by the memory management unit. This creates a potential for hardware capability misalignment, where AI-specific access patterns could theoretically bypass standard software sandboxing. However, this is a theoretical risk based on older architectures like the A18 Pro or the neural engine exploits found in iOS 15 and macOS 12. It is not a confirmed reality for the unannounced M5. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The story you are hearing about, Anthropic AI gaining root access, is not about a broken chip. It is about a legitimate tool called the Anthropic Computer Use framework. This is a system designed to allow AI models to interact with the graphical user interface of a Mac. It grants the model authorized, high-privilege control over the file system and GUI to perform tasks on behalf of the user. When you see reports of an AI gaining root access, it is because the developer explicitly configured the tool to have those permissions. The AI is not exploiting a flaw in the silicon. It is executing commands through the accessibility APIs that the operating system provides to assistive technologies. This distinction is critical for your security mindset. The danger is not that the hardware is broken. The danger is that the software-defined access permissions are too broad. We are shifting the threat model from traditional software logic errors to a scenario where the tooling designed to accelerate development inadvertently probes and exposes system boundaries. The AI is not finding a hole in the wall. It is being handed the master key by the building manager. The narrative needs to shift from a hypothetical hardware exploit to the tangible risks of autonomous agent authorization. Consider how this changes the way you should think about memory safety. In the past, we relied on software patches to fix buffer overflows or privilege escalation bugs. Those are logic errors that can be corrected with code updates. But if we assume that future memory safety guarantees for AI workloads can rely solely on software patches, we are making a dangerous assumption. The root cause of potential future issues lies in the hardware's design choice to prioritize performance over strict memory isolation for neural processing units. The neural engine is built to be fast, and speed often comes at the cost of the same rigorous isolation we apply to general-purpose CPU threads. This discovery, or rather this realization, marks a paradigm shift for AI practitioners. Security boundaries must now be re-evaluated not just at the operating system or application layer, but at the silicon level, where AI accelerators execute unverified tensor operations. We are seeing a new failure mode where the very tooling designed to accelerate development can inadvertently expose hardware-level misalignments that human engineers might overlook. We tend to assume that hardware is a static, secure foundation. We assume that because a chip is made by a major manufacturer, the memory regions are perfectly segregated. That assumption is becoming a liability. The use of AI models to discover these potential vulnerabilities highlights a new dynamic. The AI is probing the system in ways that human testers might not. It is testing the limits of the accessibility APIs and the neural engine's interaction with the kernel. If a future M5 architecture integrates neural engine memory isolation with AI agent permissions poorly, the result could be a system where the AI can read or write memory it should not access, simply because the hardware allows it to do so for performance reasons. This is not a bug in the code. It is a feature of the architecture that becomes a bug when the permissions are not aligned with the security requirements of the task. So, what should you take away from this? You must recognize that the current security risks are software-defined access permissions, not architectural failures in the unannounced M5. The knowledge gap remains regarding how future M5 architectures might integrate neural engine memory isolation with AI agent permissions. We cannot benchmark or analyze this yet because the chip does not exist. However, the principle is clear. The danger lies in the AI's ability to execute arbitrary commands via accessibility APIs, a feature of the OS interface, not a misalignment of the neural engine's memory management. As you move forward with your projects, do not assume that the hardware will protect you from the permissions you grant. The hardware is a tool, and like any tool, it is only as secure as the way you use it. The shift from viewing security as a software problem to viewing it as a hardware capability alignment issue is the most important lesson here. You are no longer just writing code. You are designing systems that interact with silicon in ways that can bypass traditional safety nets. The future of AI security is not just about patching bugs, it is about understanding the physical limits of the machine you are building on. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.